adiabatic. Yes, read this adiabatic theorem. There's one thing I'm very interested in. I'm planning to work on it as soon as I have time. No, that's not a good way, because then that would be never. But at some point, if you think of the adiabatic theorem, the way we phrased it is we start from the ground state of some Hamiltonian, some eigenstate, right? Which is, in the end, is just a 2 to the n column vector, right? So in some sense, this is just a probability distribution of a 2 to the power n points, right? Because each amplitude squared is a probability. So we start from the ground state. So we start from the ground state of some Hamiltonian. We end up in the ground state of some Hamiltonian. So phrase this sentence in a probability way. We start from a distribution. We end in another distribution. But we do that in a very specific way, which is following the ground state of our time-dependent Hamiltonian, of our time-interpolating Hamiltonian. In fact, if you remember, I had this function r of t, which r of t is 1 minus t, or t. You could take other functions, like continuous, starts at 0, finishes at 1. This is called the adiabatic path. Now, there's something which I think is very interesting, yet I haven't found anything on it. So if a strong PhD student or postdoc is interested, I start from a distribution, I end in another distribution. This we know what it is, right? This is optimal transport. But it's optimal transport in a very specific way, and in fact, in a very computational way. So I think there is something interesting, which is actually to make the link precise between this formulation and an optimal transport way. Does that correspond to some particular optimal transport map? I don't know, right? This is just one question mark that I started working on a little bit, but I don't have any answer yet. Okay, so what do we do now? Yes. So we want to do quantum machine learning at some point. But first of all, we need to think about how do we encode our data. So we have data. Again, we don't do quantum finance dilly-billy thing, right? We do quantum computing, but we have real data. So real data is X. Of course, there's one very simple way of doing it, which is, well, I approximate it by X hat, and then I do a binary decomposition of X hat. So something like 2 to the k, alpha k, equals 0 up to n, plus some beta k, 2 to the minus k, k is 1 up to m. Right, that's a binary decomposition where all the alphas and the betas are in 0, 1. Right? And therefore, I can construct the state X hat by whatever they are, alpha n minus 1, alpha 0, beta m, beta 0, beta m. That's a very basic way of doing it, right? But of course, it means that, well, I will need n plus 1 plus m qubit for one real number. It's clearly not efficient, right? And of course, data are not just real numbers, but vectors and matrices. So this is a basic way of doing it, but let's do that. This is stupid. We try, right? But clearly, especially given the current NISQ framework, which is noisy intermediate scale quantum computing, where we don't have that many qubits available, this is pointless. Another way of doing it which is more efficient, which is, well, now take your data, map it to 0 to pi, and then what I can do is I can do angle encoding, right? So which is what? Which will basically, for my state 0, I will, this is x, and let's say some gate, let's say y. Maybe let's call it theta, just to not to get confused, right? So now my new quantum state. So we already did this computation, but let me rewrite it again, but this time with the y gate. And there's a reason why I take the y gate here. So y gate actually looks like this, I think. Minus I 0. Right, so this is, so it means what? It means the y applied to 0, this gives me I 1, and y applied to 1 gives me minus I 0. So, and this means what? This means that this is cos theta over 2 identity plus I sine theta over 2 y. Apply to 0. And now this is cos theta over 2, 0. And then y applied to 0, this gives me I times 1, the I squared, minus sine theta, sorry, we got the 0, minus sine theta over 2, 1. So that's very handy because now, of course, my data is encoded not into the quantum state, but into the amplitude state. One thing I want to emphasize here is that the way the data is encoded is nonlinear. Obviously, right? From theta, you get to cos theta or sine theta. So in fact, but now, of course, depending on the data, you have, if you have 2 points, theta 1, theta 2, did you get 2 qubits? Maybe, maybe not. Maybe you could add 1 layer with, maybe you could have this, E I theta 1 over 2 y, and then E I theta 2 over 2 with some other one, Z, for example, where theta 1 and theta 2 will be encoded through successive gates. I don't necessarily need n qubits for n data points. Again, it depends on the data you're looking at, and it depends on the problem you're looking at. But this, so yes, so this is the data encoding problem. Now let's look at, let's do what we want to do. So we want to do look at quantum neural networks, and just for Chris, we want to look at quantum kernels. He likes kernels. Okay, let's start with quantum neural networks. That will, in a way, be very easy. So, as I said, I'm not a neural network guy, but so it looks like this, right? I start from x's, and then I have stuff like this. This is a classical neural network, and then I have y's. So this is x, this is y, and then you have all these things like this, whatever they are, blah, 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 blah. This is my understanding of a neural network. You get the idea, right? We've all seen these pictures. A lot cuter, obviously, with colors and all that, right? Now, the point is, this is a linear map. This is linear map. This is linear map. And then I have activation function. Let's call it sigma, sigma, composition, composition, and therefore y. Right? So y basically is some nonlinear map of x. Right? And the point is, I have, if I add layers, that it's a lot of non-linearities. And I'm able to, of course, I have linear, so I have hyperparameters, right? And I optimize, then I create a loss function, right? So I have a loss function, which would be some sum of phi over my training data, y hat, I, y d for data, squared over I. And then I minimize this, and of course, phi depends on theta, which are all the hyperparameters, and I want to minimize this over theta. If I understood neural networks, that's roughly what it looks like. Right. So how do we do this in a quantum context? So, of course, we have to change things a little bit. So here, I will need, X is my real data. I need to encode my data. Right, so I will have a layer. So I use blue for the quantum part. And the black is the classical way. So there I have some encoding part. And so the encoding part, let's say, is something like R U of X. RU of X is rotation according to some unitary operator U with angle X. So here X is a vector, right? So either I can do it with several layers of encoding, right? But I know how to encode data. So EIX1 y over 2 multiplied by EIX2 over 2 times z and so on, right? So I encode my data in some particular way. Then, so the only way I can create a circuit is by unitaries, right? So now I don't have all this part. I don't have all these arrows. I just have, see this much easier because I just have a horizontal line, much easier to draw. Then I have one big box, which is U. And then I have Y. And then I have big measurement box. So what does it mean? Here, we do the encoding. Now this U is a big unitary matrix, big unitary operator that acts on it. So it depends on vector of, I can parameterize with some parameters theta or hyperparameters theta. Of course, how do I choose it? Well, you might want to make it hardware consistent, right? So something of the form, let me do it here, for example, U of, let's say, vector theta would be something like this. We said we only allow it to pairwise entanglement. So something like this, right? Where I have my qubits and I have pairwise entanglement, because otherwise I don't know how to entangle with 3 qubits really. Maybe I can also add some other matrix as H here, and this one depends on theta 1, this one depends on theta 2, depends on theta 3. Which architecture is optimal? There's no answer. Of course, to me, it's exactly the same as if I have a classical neural network. Should I take, 3 layers, 10 nodes, or 15 nodes and 4 layers? You try. Sometimes it works, sometimes it doesn't work. So now here at this stage, let's not call it y. At this stage, this is a big quantum state psi of theta, which depends. So theta is the vector of all thetas. Of course, that also depends on the data, x, which was encoded here. So now, okay, now I need to define some loss functions somehow. That depends on the problem you're looking at. So suppose that the problem you're looking at is classification problem. So x is height, weight, shoe size, I don't know, something like that. And y is man or woman, right? Male or female. Then my y has 2 data points. So maybe, because if I measure this, I end up with a probability distribution. And maybe I don't care about the whole probability distribution. I could only measure 1 qubit, for example. And that gives me a probability of being 0 and probability of being 1. Whatever qubit 0, qubit 1 mean, right? These are just labels. But then, if I only measure not the whole thing, but let's say only one of them, right? So then, of course, this means I will have something alpha 0 plus beta 1. But of course, alpha and beta depend on theta and on x. So then, my loss function could be, well, ascribe alpha to being, 0 to being male, 1 to being female. And so, I will minimize over the data. The data are all the yi, and 5xi are the alpha and beta. That's one way of doing it for a classification problem. Now, there's another way of doing it, which is if your output is not just a classification problem, but a function of x, right? So you really want to learn a more complicated map. Then, of course, if your output is a probability distribution, it's not clear how to write it, how to write the equivalence. But we know, we did that earlier, we know how to compute this thing. We know how to compute the expectation of some observable. So this, of course, this is a function of x. Function phi that depends on theta. Right? So if my objective function is the expectation of the observable, then I can use this in my minimization problem. Right? This is a target function, and I want to equate it to the true function I want to define. So I don't want to write too much detail there because the function you're trying to obtain at the end depends on the problem you're looking at. If you look at a classification problem, or if you want to learn a general map from x to y, well, one is, okay, if I want to observe a probability distribution, if you want to do, for example, GAN type of problem, there is a version of quantum GAN, for example, where you want to get a probability distribution. There, where it's simple, you have n qubits that will give you 2 to the power n points. Then you want to match all the amplitudes or the probability at the end. And so then, as loss function, you will take, some Wasserstein distance between your output probability distribution and your target distribution. If, in fact, this is a nice thing to do, quantum GAN, because if you write this in terms of the quantum version of GAN, actually, everything is a convex minimization problem, actually. So it has very nice properties. If you have a classification problem, then I measure 1 qubit, and that gives me alpha and beta. One point about this is if your classification problem is linear in the data, this will be very bad, because alpha and beta basically are cos and sine of the data, and because of the way we encoded the data. So if your classification problem is linear in the data, this would be extremely bad. However, if your classification problem is not linear, that could actually be handy without having to do kernel stuff. If the map you try to learn is the function of the data, then you can write it so either as an expectation like this, or you can also encode it in this way. In fact, let me write a theorem or meta theorem, let's say. So I don't know. Just quickly, actually, I should have asked who's familiar with neural networks and machine learning vaguely. Okay, most of you. So there is, for example, a quantum or some quantum versions of universal approximations theorems. So let me state one version. Okay, I state this version because this is a paper I wrote with Lucas Gonnen. So at least I know this version. But it's nice because it's quite simple, actually. So what it says is that something like this. You have a target function f hat theta n. I will explain this in a second. Mu dx, some L2 norm. Some constant. So what is this? So f is, if you have some function, this is actually over Rd. So the constant here, so I want to approximate, so mu is any measure. Right, so in fact, I could forget, I could write just dx. Doesn't matter, it could be just a Lebesgue measure. But you can make it a bit more general. Let's say we only look at this. The constant c, actually the constant c, I can write it explicitly. This is the L1 norm of the Fourier transform of f. So if I have a function f with Fourier transform in L1, then we can construct a quantum circuit with n qubits, and there exists a vector of hyperparameter theta such that, so I didn't say how I computed f hat, but essentially, this is not exactly what this says, but this is similar. Basically, f is the expectation of some observable. So I can construct a quantum circuit where I encode x, the data x, I encode, and I have a vector of hyperparameter theta that will allow me to approximate any function f with Fourier transform in L1 with this error bound. Why is that important? Because take, for example, so we're trying to work out, so the paper is already on arXiv, but so we're working on subsequent follow-up, which is, okay, take, for example, f of x is Black-Scholes, gold price. One important question from a very practical point of view is, let's say Christian works for the bank. I can picture him working at Goldman. He has the type of the Goldman quant guy. Right. So he works for Goldman and he's thinking, oh, I'm head of quants. Should I invest in quantum technology or not? Of course, that's a very general question. And in fact, that's not the right way of asking the question. The right way of asking the question is, I'm pricing loads of options every day. Can I compute my options in an efficient way? This tells you if I have my option surface, all my strikes and maturity, and I want to be, epsilon close to the true solution, how many qubits do I need? And what's the depth of the corresponding circuit? If the answer is, oh, I need 5 qubits and depth, which is 10, and then I ask IBM, can you build this? The answer is yes, then okay, that's great. If the answer is to get epsilon, I need 10,000 qubits and a huge depth, it means I have to wait a few years. So the exact answer, you have to wait a few months. We're working the details. The point is the quantum circuit we build, we can actually implement it. And so now we're trying to work out some specific examples. But there are different versions of universal approximation theorem, but this one at least has a narrow bound, so it tells you, the cost and when it should be feasible. Yeah. Root of n. Yeah. It's badly written, but this is n. Here, n is the number of qubits. So basically, the circuit is 0, 0. I have 10 of them. Then I have a big U that depends on theta. I have a layer of encoding here, x, and then I measure. But n is the number of qubits. So there's no activation function, right? In fact, so at first, there was something very confusing to me when I started looking at this quantum neural network, because the whole point of neural networks, to me, classical neural networks, is the activation function creates some nonlinearities, and I have many of them, so that I can approximate anything in a loose way, right? Now here, all the operations I perform are linear, right? It's unitary operators, it's linear. But in fact, it's linear, sure, but I encoded the origin data in a nonlinear way, through amplitude, through cos and sines. So in fact, there's no equivalent to activation function, but I don't need activation function because the nonlinearity is already in there.
A hidden Fourier representation in this one, then.
In what sense?
In what sense that the things are linear and maybe I don't know the details, right? But you're using sort of rotations in the complex plane. So
yeah.
Could it be that this is connected with a Fourier integral representation, and then from here?
I mean, there is some Fourier thing because the way we actually prove this, that we have a Fourier transform, right? The bound depends on the Fourier transform. So the proof we have is based on the paper that Lucas had before in the classical case, which used some Fourier approximations. So of course, I mean, because we're looking at exponent I something, there's a Fourier part, but no I'm not sure how to answer the question precisely.
But looks exactly the
Yeah.
same.
Yeah. I mean, this is what we're using, right? But, and in fact, we have another version, which is also as part one of the paper, part two of the paper, which I like even more, which is to do reservoir quantum computing, which says that, because of course the problem with classical neural network, the problem here is you have to train, right? And if I have loads of parameters, hyperparameters, this is hard to train. So in fact, what you can do is you can build tilde here. Where now the thetas are randomly pulled from some prior distribution, so you don't train them, and then you optimize basically linear regression over the last layer. And you get the same bound with an extra constant, which I don't remember exactly. But
So these are random features essentially.
yes.
But you don't train the frequency.
No.
Would that improve things if you train the frequency?
Maybe. I don't know. I haven't tried yet.
Can maybe discuss later.
Yeah, of course.
Some.
So, okay, so where do we stand now? What else do we want to talk about? Talk a little bit about what's the other course is what? I mean, it's kernel signature. That's the keywords, right? Okay. Maybe I talk a little bit about kernel stuff, right? Okay. So I want to talk about two things. I don't know. I have to, I get lost in these notes anyway. I want to talk about quantum kernels quickly, and then I want to say a few more things at the end about noise. So kernels. Okay, let me look at a simple version, which is support vector machines. Okay, so I have to be careful because if I say something silly about kernels, Chris is not going to be happy. Okay, so my understanding of this is you want to do, this is the picture I have in mind. You have loads of data. I can start. And you want to do this. That's how I understand the problem. I like pictures. Right, so what it means is I have loads of data and I want to linearly separate the data. Right. So what it means is I want to, so there's something called the functional margin, I think. Which is the yi, so of course this is x and this is y, right? X and y. Yi is, no, gamma I is yi wxi plus b. So here I look at linear classification. So yi basically is not, this is not really y. Yi takes values in -1 plus 1. Right. So either I'm below or I am above. And you want to linearly separate data. And so the problem, and so basically, when this is positive, it means it's good, it's well separated, and so it's on the good side, and if it's negative, then it's on the wrong side. I see Chris doing this, which means what I'm saying is correct. Right, so because this is positive, then I'm happy. If this is negative and negative, I'm happy. But if the product is negative, then I'm wrong. Right, I should be on the positive and I'm on negative. I should be on there and I'm there. So the problem is what is I would like to do what? I want to minimize all the gamma i's. I want to minimize gamma such that all the gamma i's are greater than gamma. Let me take my note just for this one. No, see, I got that one. Okay. I want to maximize this. Right. And the gamma is the minimum of all of them, right? So gamma here is the minimum of all the gamma I. Yeah, that makes sense, right? Because gamma is smaller than this one, and this is my optimization point, right? So the functional margin basically is for each point, gamma I will give me, one line, and I want to find the one that really separates the data as much as possible. Right? I don't want to have this line here. I don't want to have this line here. I want really to have the one that separates the data as much as possible. Right? So this is this largest gamma, such that all the gamma are greater than this one. But okay. So if I normalize things a little bit, so if I divide by the norm of W, this means all the gamma i's are greater than 1. And this should be gamma tilde, but I'm not writing the tilde, right? So I divide by the norm of W, basically. So maybe let me just rewrite it. This means I want to maximize gamma, let's say hat, over norm of W, over gamma I greater than gamma, what is this? Than gamma. I always get confused with that one. Oh yeah, I just have to write this tilde, gamma tilde, right? Okay, so then, of course, this is the same as minimizing W. I get confused with these notes. Sorry?
What was the tilde notation? I missed the tilde.
Okay, let me rewrite it. Maybe easier. Sorry about that. So I want to do what? My constraints are all the gamma i's have to be greater than gamma, right? And I want to maximize over gamma. I want to maximize gamma. That's the original problem. Now, if I divide by, this is the same as max of, I divide by the norm, right? So, the norm squared, So in the end, what do I get? I always get confused with that one. It's not the first time. If I normalize by W, I divide by W, but because all the gammas are greater than 1, then this is the same as minimizing W, right? Because it's max of gamma over W. So this will be the same as minimizing W, or W squared, right? Subject to all the gamma i's being greater than 1. Right, so tilde, right? So I divide everything by norm of W, or W squared, right? So this means that this would be 1. I have gamma over norm of W, but max, if gamma is fixed now, then this is minimizing over W, right? But of course, it doesn't change anything. If I put 1/2 here, it just makes it easier. Do I have the same thing here? Yes. So why am I saying this? Because then I'm not going to write all the details here, but of course, this I can write the Lagrangian, right? Which is this function minus sum of lambda I, gamma I minus 1. Then the gamma i's, I can replace them here, right? And if you do this, you end up with this problem, the max of, let me write it, W alpha, where W alpha is what? Is sum of alpha I. Alpha I are the Lagrange, what are they called? Multipliers, sorry, minus 1/2 of the norm of W star squared, where W star is just the sum of alpha I, Y, I, X, I. So W star is just, I take the gradient with respect to W. That just give me W, and here I have W. So this is the W star solves gradient of the Lagrangian being equal to 0. And then the other term here, you get it by taking the gradient of this with respect to alpha, which are the Lagrange multipliers. So this is just a few lines of computation. So, okay, why am I mentioning this? Because the one thing that's important here, well, the two things. One is to the linear separation, right? It says, I want to find one line that linear separates the data. In the end, the key part you have here is this object here. But this is what? This is an inner product, which is not a very exciting one, right? But this is an inner product. Now, suppose the data is not, you cannot separate it, right? So you cannot do this. So the classical example is that I can try to do it. I can try to do this. The simple example is this, where I have data like this, and I have data like this, blah, 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 right? Then, of course, I cannot linearly separate, but I can say, oh, whatever is, below the circle here, I add a dimension, I put it, higher dimension, and then I can have a hyperplane that will separate the black and the blue, right? So let's say we're on a flat, right? I have the blue and all the black one, I put them up there. And so then I can have a hyperplane that separates everything, right? So this is the picture version. Now the general version is to say, well, I'm going to create a kernel map, which will basically map from x to phi of x. But now phi of x lives in a higher dimensional space, right? And now what I'm going to do is I'm not going to solve this problem with x, but I'm going to solve the problem in my higher dimensional space, in the phi of x space. And the only thing that really changes, actually the whole computation is the same, except that here, I'll end up with yi phi of xi. Yeah, this is exactly a feature map. Kernel feature. Well, okay, I haven't talked about kernel, so I shouldn't say kernel. because then I can see it's being grumpy. This is a feature map, right? You have your data, and your phi of x is the feature space, right? So I think this is what I wrote here. Maybe. Now the problem, of course, is okay. How do I actually compute this inner product? Right. Exactly. See, here's the solution. Because as Chris will tell you, computing inner product is actually difficult classically. I'm just quoting him, right? I'm not sure what that means, but I'm quoting him. So if you disagree with me, just ask him. But the reason I'm mentioning this is because, in fact, computing kernels is something that's very easy to do on a quantum computer, at least in principle. And so I say quantum kernels, or computing quantum kernels. So suppose I want to compute this, right? So let's say phi of xi, phi of xj, right? So this, of course, in general, they would call it k of xi xj, right? So this is a semi-positive definite matrix, right? So this is a valid kernel matrix. But now, okay, so if I want to do the quantum way, there are two ways of doing it. One is, again, I need to think about what phi means here. Phi is the way I encode the data. So in fact, phi, if I think of phi of x in this way, so here I want to understand this object, right? But then I can actually say, well, this is phi that's parameterized by theta and phi parameterized by x applied to 0. Right. Again, I have my quantum state 0. I encode the data through x, and then maybe I have some extra theta. We can even forget about theta here and just think of it this way. Right. And we saw how to encode the data. And maybe if we want to, can even write ux, really emphasize that everything is quantum, does this really apply unitary operators? So here, this is what? This is simply the 0. This is u dagger xi, u xj 0. So, okay, so how do I compute this? How do I compute this? Well, my claim is this, that if I use this circuit, sorry, I go here first, no, the other way, sorry. So I first apply xj, and then I apply the other one. And then I measure, and what I'm claiming is the probability of observing 0 is what I want. Well, if you remember, the probability of observing 0 is what? Is the state psi times the projector onto 0, which we call P0 psi, which is what? Which is psi. This is just the 0, 0 psi. Which of course is psi 0 modulus squared for any quantum state. So now my quantum state psi, I know what it is here, right? here psi is u dagger xi u xj applied to 0. So if I try to compute the inner product of, let's say, 0 and psi, right? What am I doing? Well, this is exactly what I have here, right? In fact, I have z because this is my psi. I don't need to write anything more. This is my psi, so 0 psi is exactly what I want. This probability is exactly computing the circuit and measuring the probability of observing 0. So computing an inner product here is actually very easy. Right? Any question on that? What else do I want to say? Yes, there's another way, actually, a more general, well, not more general, but there's something called swap test, which I'm still not entirely sure whether it's, yeah. Sure. I mean, you always have to do Monte Carlo anyway. When you measure, the probabilities of observing 0 or anything, these are theoretical probabilities. Then you estimate the probabilities by Monte Carlo. Always, yes.
Monte Carlo computation.
Well, I mean, the Monte Carlo thing is a classical Monte Carlo estimate.
Yes, I know, but I mean, what is the usual level of accuracy that you require in practice for these sort of computations that you do? I mean, what are we talking about? 10 to the minus 2 relative or 10 to the minus 4? I mean, just to have an idea how you have to push this Monte Carlo.
Well, it depends how much. I mean,
I know it's problem dependent. I know it's problem dependent, but I mean, something just to have an idea what.
I'm not sure I have an answer.
No, but you have maybe one problem in mind. You can say, yeah, sure, but for these kind of problems, or I have this example in mind.
So I mean, the example we looked at yesterday, right, where I was simulating uniform distribution, let's say over 2 points, right? Well, I run the circuit, I can't remember what it was, 10,000 times, right? And then, I mean, I'm not sure how to answer in the sense that we know exactly what the error is, right? This is classical Monte Carlo error.
Yes, I know, but I mean, I wanted just to know which is the usual level. Okay, so but why do I ask this question? You have a system here that is efficient, and all these computations ultimately rely on the estimate of these probabilities, and the probabilities are relying on this Monte Carlo running. Yes. Okay, so you could say, okay, I usually do these computations on a level that actually the Monte Carlo step requires, I don't know, 10 to the minus 3 relative accuracy, and then I know more or less where you're going. Or I use it in such a crude manner that actually 10 to the minus 2 is usually fine for all the things that I do.
I mean,
so I want to know, these kind of things, because this tells me more or less what is the
But to me,
behind.
To me, it's more, you should tell me, the accuracy you want, yes, and then I'll tell you how many runs you need to do.
Okay.
If you tell me I need to do 10 to the minus 3, then, you need to do 1,000.
I mean, maybe the question that Raul really wants to ask is, how long does it take to measure? How long does it take to to get one sample, one measurement?
Yes, this depends on the circuit, right? In the sense, if the circuit is very deep and has a lot of qubits, it takes more time, of course. But it also depends then on. So I can answer. No, and yes, this time it's me. If I take superconducting qubits, I know that takes 50 nanoseconds, right? So if I have Hadamard with 1 qubit, I have 1 gate. At 10 to the minus 9, 10 to the minus 6, 10 to the minus 5 seconds. At the one before, 10 to the minus 5 seconds. But to get 1 sample. So the measurement has 0 cost, right? So 10 to the minus 5 seconds to get 1 sample. No, 10 to the minus 5 seconds to get 10 samples. Right? I guess you're in the middle of the desert. You can't go in. We can't. The important sampling here. Yeah. I mean, because if you change the basis, you can change the basis in which you compute, right? Because then just means you compute, with a different probability measure. But then, of course, changing the basis means adding gates. That has a cost. So actually performing the important sampling has a cost. I don't know.
But formally speaking, you have many different quantum algorithms to compute the same thing, right? So important sampling in a way, abstractly, just means you choose the quantum algorithm for your specific problem, which leads to the smallest variance.
But then you can, because if you have a quantum algorithm that gives you more variance, but running the algorithm, it might mean a lot of gates. Yeah. 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 Yes. What was I saying? I don't remember. Yes, I know. So there's another way of computing swap test. There it is. Suppose I want to compute this thing. So I have 2 quantum states, and I want to compute the inner product. And there's a very neat way, at least theoretically, mathematically, which is very pretty, but it's also very informative. That's why I want to mention it. So I'm claiming, what am I claiming? I'm claiming that if I build this circuit, I think, phi, okay. So I'm claiming that this circuit, that this is equal to the probability P0. Okay, so let me explain a little bit. Sorry. So quantum state phi, quantum state psi. They can be of any dimension, right? Phi can have many qubits, right? This funny gate here, this is a control swap gate. So it's a 3-qubit gate, which of course I started yesterday saying, oh, we don't want them. But this one, it's actually feasible. Not always, but it's partially implementable. And a control swap in the sense that, again, the first one is the control qubit. So if it's in 0, I don't do anything. If it's in 1, I swap the 2 qubits. And then you see I measure only the first one. So the outcome is alpha 0 plus beta. So here it's alpha 0 plus beta 1, and the outcome I measure only top qubit. So why is that informative? Because usually this will be called an ancillary qubit, which is I can add qubit to help perform the computation, even though in principle it does not appear in the first thing. But you have a lot of quantum algorithms that for which you require additional qubits for temporary computations. So maybe let's try to prove this. So, okay, so I start with 0 phi psi. That's easy. Then I apply Hadamard. So I've got 0 plus 1 over root 2 phi psi. Again, I'm not writing, but these are the products, right? As usual, between states. And then, okay, so then what do? I apply the control swap. So if the first qubit that's the control one is in 0, I don't do anything. Okay, so everything is linear, so 1 over square root 2. If it's in 0, I don't do anything, so I have phi psi. Plus, now if it's in 1, I swap. So the control doesn't change, but then I swap, it's psi phi. And then I apply Hadamard again to the first qubit. Maybe let me just visually write this one in red. So apply Hadamard. So the 0 will become 0 plus 1 over root 2. 1 will become 0 minus 1 over root 2. So I'll get 1/2 here. And then let's just run like this for now. 0 plus 1. And then 0 minus 1. Boom, boom, boom. Phi psi plus psi phi. And then if I regroup everything, I have phi psi plus psi phi. Apply to 0. Plus something I don't care. Apply to 1. Well, I don't care because in the end I measure only 0, so the inner product of 0 and 1 will be 0, so that will disappear. I realize that this comes out very big on the screen, but okay. So this is my quantum state here, right? Right now I'm here. And then I measure, and I want to compute P0. Actually, I can do this. I can do this thing. No, this. It's thinner. T0, then what I need to do is, so this is my state, let's call it big phi. That would be big phi. Then the projector, big phi, right? Of course, because I apply 0, so now my big phi has, you know, what did I say? Oh, sorry, there was, it does happen, right typos, right? The 0 should be on the left. Thank you for telling me now. The 0 should be here, right? Apologies for this. 0 there, and then plus 1, blah, blah, blah. Sorry about this. But then, okay, when I apply 0 to phi, so if I only look at this part, right? This part will just give me this one, because this one will disappear. And likewise, when I take the transpose, we'll get this one squared and I sum and basically do the computation, you will get 5 psi. Right. So in fact, this swap test is very convenient because if you give me any 2 quantum states, no matter how you generated them, I just need 1 extra qubit, 1, to compute the inner product. Okay. So what else did I want to talk about? No, this we said. Ah, yes, we'll talk about noise. Any question on that? So now, of course, I mean, the way you encode the data could be of any form, right? So of course, there we looked at simple vectors of data. You can think of that would be the course tomorrow, and tomorrow is Tuesday. Tomorrow and next course where Chris will talk about data that comes. I don't know. Talk about streams of data and path. Yeah. So the data could be a path, right? Then of course you do signature, right? And which are a way to encode all your path, right? Then you can of course compute kernels on the level of signatures, but then of course you can do quantum kernels. So you can try to compute quantum version of signature kernels, for example. It's in progress. We're working on this, but it's in progress. At least at this stage, as long as you are able to encode your data through a quantum circuit, then computing the kernel should be fairly easy. Right. With the swap test, it's simple. You just add 1 qubit. Trying to think if I anything else to say on this. So how much time do I have? 20 minutes. So the last thing I want to reaching the end of the page. So the last thing I want to talk. So everything I've said so far, absolutely everything, was about started from postulate 1, we closing the loop, which was the closed quantum system can be associated to a Hilbert space, and any quantum state can be seen as a ray in this Hilbert space. That was postulate 1. Closed system means what? Closed system means there is no interaction with the environment. And closed is there's a physical physical way of understanding close is right now, it's in a big fridge in absolute zero, and the fridge is closed. If you open it, then there's a lot of noise and perturbation, then you lose the absolute zero, and so then the qubits decohere very quickly, and the computation is useless. But of course, there is noise, right? And the noise is not noise. So earlier today, I said, well, we can use noise in this quantum annealing setup to help us. But the reality is you do have some noise in the system, right? If you remember this table I showed yesterday where we had gate fidelity, for example, which was 99.9%, for example, for superconducting qubits, and roughly the same order for ion traps. It means that every time I apply my quantum gate, whether it's Hadamard or Pauli Z or Pauli X and so on, I do lose a little bit. 0.05% of the cases, it does something wrong. I also have the fact that the qubit, even if they take 15 microseconds, even if the decoherence time is 50 microseconds, even after 10 microseconds, I lose a little bit. Maybe not so much, but a little bit, right? So how should I think of this noise? How should I add this noise? And so there's a concept, so now it's called open quantum systems. I prefer with a sticker. There's this concept of open quantum systems. And essentially, the idea would be, I have a quantum state, but it's not, how do I phrase it? It's not ideal. Not ideal in the sense, the quantum state itself, I cannot view it as a closed system, as living in a closed system. Yes. So, for example, so it means that I have a classical probability, let's say 99%, that my quantum state is correct, but 1% where it's not correct. And I mean this 1% and 99% as classical probability. So in fact, my quantum state is not of the form alpha naught plus beta naught, alpha 0 plus beta 1, but its quantum state is mixed. A mixed meaning as opposed to pure. So these are real terms. Meaning it's actually in a collection of pi psi I. And these pi are real probabilities. Think of two cases, right? There's not in 99% of the cases, yes, correct, right? But 1% is wrong. So it's in a mixture of states, if you wish. Now, this formulation makes it actually not very easy to work. So the general idea is what? The general idea is, you can think same as feature map, which is in fact these classical probability come into the picture because there's the environment which creates noise. Then I'm going to look at the combined system of state plus noise, put them all together as tensor product, and the whole thing will be a closed system. But it's not really easy to write in terms of quantum states. And so there is another tool, and you can rewrite everything in terms of what's called density operators. The density operator, so if I have, let's say, a pure quantum state, which is what we saw before, psi, then rho is just the outer product. Right, so it's a matrix. It's a Hermitian, obviously. And it's so you can actually rewrite everything in terms of density operators. So, for example, let me just look at one. If I look at Schrödinger equation, for example, let's say time independent Hamiltonian. Then if I look at dt rho, so that would be rho of t. Right, let's write rho of t. Was this a dt of psi of t psi of t? Okay, so dt psi of t, that's easy. That's minus I h psi of t. And then, okay, maybe let's do it here. Okay, dt of this one, well, I do minus I, but then I take, well, let's write it like this, minus I h psi of t, everything dagger. So minus I becomes I, h dagger, h is Hermitian, this is just h psi of t. Right? So then I multiply, oops, and of course I have the h. Okay, so this is dt times this, so this is derivative of f times g, this is f prime g plus g prime f, yes? Yes. So this I multiply by psi of t plus which is minus I h, where this one is u, this is just rho, t plus psi of t times this is an I, psi of t, and I have psi of t h. And what is this? This is just minus I and the Lie bracket of h and rho t. Because again, this is just full. So you can rewrite everything in terms of density operators, which in fact, from a math point of view, is much handier. Of course, if you think of the way we added noise before, then when I make this h add some epsilon in the Hamiltonian, then I will have this. So if h epsilon is h plus some epsilon term, then I will have this plus some epsilon extra term. But now, okay, I have 10 minutes, that should be enough. You fine with this page? Go back, because I need this. So there's, why am I mentioning this density operator? There's one particular reason, which is what? Which is, so I have rho of a system, of a state. That's my quantum state. But we said this quantum state can have some noise, right? So I'm going to couple it with the environment. In fact, the coupling of the environment will be, I take the tensor product of the density operator of the quantum state and the density operator of the environment. And so I can call this rho. Now the advantage is this rho lives in a closed system. Rho S itself is in an open system, but if I couple it with the environment, it's a closed system. Right. Now, of course, you perform computations, right? In the end, you don't care about what the environment looks like. You know how to perform operation for rho, right? Because it's a closed system. So if I have a closed system, so psi, let's say, is U0, then rho, by definition, is psi. But this is what? Psi is just U0, and then 0 U dagger, right? Which is U rho U dagger. So this is, let's say, a closed system. So if I perform unitary operation on my quantum state, I know how to translate them into operations for the density operator. The problem is I don't know how to manipulate my quantum state if it's not in a closed system. I only know how to manipulate in the sense performing operations on the closed driven by rho. So now the question is, I start my quantum system in 0, and let's say the environment doesn't move, right? So I have fixed environment, I couple it, and then rho at time t is, U rho 0 U dagger, because I perform some computation for the whole closed system. The question is, how do we recover the state of the system at time t? Right. Because we don't have a theory that tells me how to evolve open quantum systems directly. I only know how to evolve closed quantum systems. And, well, we don't have a theory. We do, but not directly. And the answer is, there's something called a partial trace. Yes. At time 1, at the next step, whatever. It's just a star, then I'll do something. Yes, in the end, it's conditional expectations. Because, so let me just think how to write it properly. If I look at, before talking about partial trace, if I look at the expectation, so I have a measurable, and I know what this means, right? I have a state psi. This is the expectation of the measurable, of the observable, with respect in the quantum state psi. Of course, this is a real number, right? Great. Yes. If this is a real number, we're going to do exciting math. This is the same as the trace of the number. Okay. But now trace has many properties, right? I can also write this m psi psi. Trace of A B transpose is trace of B A transpose. And this cyclic property, which of course is the same as m rho. But this is for a closed system, right? Now, somehow, I would like to trace out the environment. And in fact, this is exactly the same as saying, oh, doing this in expectation, I'm going to compute the expectation conditional on the environment. And so the partial trace is therefore basically conditional expectation with respect to the environment. So this is, so trace, that's why E for the environment of, what do I want? Of, so here, let me just write row, right? So here that was, okay, row 1, right, for example, the state you're looking at, right? And the way to do it, it's not surprising, right? You take this basically. Over all alpha, which form the normal basis of the environment, right? Because these are all expectations. I can add the M if you want to, just to be consistent with before. These are all expectations when I freeze the environment to be in state alpha. These are conditional expectations with respect to alpha. Right. So as I don't really have much time. So this is called open quantum system. So there's a whole theory about this. Now, of course, how should you do it in practice? Again, the best way to do it is go talk to Rigetti, go talk to IBM, and ask them, what kind of noise they actually have in the hardware. And they have precise way of, they observe the noise, right? So practically, just let me give you in 2 minutes some very quick examples. Yeah.
So this is like a nuisance parameter that you're marginalizing over and over out, and the vendor provides you the sort of distribution of this noise, and you just take it as it comes somehow. And
sorry, I didn't hear the beginning.
No, this environment noise somehow.
Yeah,
is like a nuisance parameter. The vendor gives it to you characterized by a distribution, and somehow every time you do computations, you try to marginalize this out and out and out.
Yeah, but so so for example, noise could be where they observe that in 0.01% of the cases, a bit gets flipped to 1 instead of being 0. So, but usually, they write it for density operators, and so they will have something like 1 minus p rho. So that's identity applied to rho plus p of some. They do 1 minus p plus p. Some. I don't know how to call it. Let me do it like this. Identity is better, and then some error. Let's call it N for noise. This is bad notation, but okay. Where these are really probabilities, and in 0.1% of the cases, 0.01% of the cases, my rho gets modified. So there's one particular example. Let me not go through this. But there are several. This is a simple one. So what I said, for example, is the bit get flipped, and this is called phase flip. Noise. The more general one is called depolarization channel. This is quite a popular one. It's popular because also mathematically we can actually compute things. So it means one thing to do is to look at many of the algorithms we looked at, and not so much has been done. I mean, some stuff has been done, but all this. So, for example, one thing we want to do with Lucas is, so this universal approximation we looked at, we have this quantum circuit. Now, if we add some noise, let's say something like this, right? And how does the error bound depends on this little p, which is the error. And how much do we lose? And what is p? Well, this we can ask Rigetti. I said Rigetti because we work in a bit with, but we can ask IBM or others, right? What's the real value of p? And they will tell us, well, it might depend on the depth of the circuit, of course, and depend on the number of qubits. But they know exactly, I mean, because they actually observe that, right? What else do I want to say? Well, I know I don't have any time. So maybe just to wrap things up. So as I said, I didn't talk at all about quantum Monte Carlo, even though this is a stochastic numerics conference, because this really relies on algorithms where you need full connectivity and a huge number of qubits to realize theoretical speed up. So this is not really achievable in the short term. These quantum machine learning and these optimization routines are already implemented and are being used, at least as some use cases, test use cases. There's a lot to do because, well, there's been a winter of quantum computing, just like there had been a winter in machine learning, because after the Shaw and Grover's algorithm, well, we didn't have any quantum computers. So at some point, well, why should I care? But now we have quantum computers, so we can write the algorithms. We need proofs because, again, there's no physicist, right? So it's fine, because many of the papers are written by physicists. So the concept of proof is different than for us. Sorry? Exactly. So that's good. That's good. I can. But it's recorded. I'm not sure who's online. No, but so there's a lot of empirical results that seem to be very convincing, but we need proofs. So, for example, this universal approximation theorem, we have a strict, clear proof that says, oh, here's the error bound. But this is one simple case. There's a lot more to do. How to incorporate noise? That's a big question. And of course, then depending on the problem you have, I'm not, as I said, a machine learning or neural network kind of person. But all the problems, 10 years, the really math part of neural network really started having strong results in the last 10, 15 years, roughly, right? With strong, clear proofs converged. I mean, there was some stuff before, but there's been a lot more in the past 10, 15 years. There's a clear pathway, which is, let's try to reproduce these proofs in this context. But it's not just copy paste, right? I mean, as you saw, the math are a little bit different, but there's a lot of things we can get inspired from them. And so the beauty is, as you saw, there's a bit of linear algebra. There's some complex numbers as well. There's, you can link it with probability and optimal transport, which is fun. As soon as you add some noise, you have SDs or SPDs. So there's really some fun for everyone. And I think that wraps it up.